Okay, now we've moved over to a different part of their laboratory. This is where they have quite a bit of the samples of the bricks that would be manufactured. And can you talk a little bit about what we're seeing here and the differences of the regolith that are on the move? Because it's not just a uniform amount of regolith across the entire surface.
Right. We have a couple of sample bricks that we've made. These were actually made in the kiln. We didn't take them to full liquefaction state and pour them. These are solid, more ceramic.
Can I pick one up?
Sure.
Is this representative of the size?
Yes.
Okay.
Yes.
So gives you a good idea of about how big these actually are, and they're fairly, weighty.
About 8 pounds.
Okay.
Yeah, about 8 pounds. And that particular one was made from a Mare simulant, which is the dark part of the moon.
Okay.
Which is volcanic based material, very much like the basalt we have here on Earth. And so we use an LMS one simulant, okay, to simulate that. Obviously, we're not using the actual regolith from the moon from the Apollo missions. That's such a finite resource.
Right.
We use simulant to represent as closely as we can what's up there. So we try to get our process down as much as we can.
So I have a quick question about that. Is how do you know what the lunar regolith is like? I know we had Apollo and they brought some rocks back, but they were kind of equatorial, and I think a lot of them were in the Mare as well.
Mm-hmm.
But what about, say, the lunar South Pole, which is where Artemis wants to go, or other parts of the moon? How do you know?
We rely on other experts. And so there's some folks who've, we have land in highlands areas. Okay. So we know we have some samples from Apollo, from the highlands. And then there's been some remote observations, some other landers. The Indian lander just recently landed in the South Pole.
Not Data 3.
Exactly. And so we have some data from them that informs our decision on the materials that go into our simulate.
Okay.
So we can try to replicate it as much as we can. There's a lot of things in these terrestrial simulates that aren't represented on Earth. There's some chemical reactions that happen just because we're on Earth. And the atmosphere or the environment that we have here, there's some chemical bonds that exist here that don't exist there. And we can't really replicate exactly what's there.
Okay.
But it's a simulant. It just simulates it. It's not exact. And so we just kind of get as close as we can. Okay. And so there is a simulant specifically made for the South Pole that experts around the country and NASA agrees with that. I believe yes, agrees with it. But this is a good representation of what's on the South Pole.
Okay.
And so we use that as our guide, our simulant as we melt and manipulate and work.
Okay, well, I think that's an important point to bring up. Simulations are great. They give you a certain degree of the way to where you need to go. But at some point, you need to fly the plane. You need to fly the rocket. You need to make the bricks on the moon. So when I was talking to your CEO earlier, he mentioned that even the very first demonstration mission for HLS with the Starship is going to have a lot of tests that are going to be taking place. And one of them is you, and you're going to actually try to see, can you get some of the regolith? Can you sort it properly? Can you verify that it has the composition that you need? Are you going to be able to, on that, make a demonstration brick, or is that a little bit farther?
No, we're not going to make a demonstration brick on that, but that's going to inform our decisions later. And all of this is an iterative process. Right. And so we were talking earlier about how we're kind of in the infancy of this. We're making it here, imagining what it would be there. And we're making our best guess. And that's what science is, that's what engineering is you take the data you have, you build a prototype, you test the prototype, evaluate the results, modify it, do it again. And that iterative process is critical. And we're at the infancy of that iterative process, trying to determine exactly what we have, what our capabilities are, how do we overcome some of the challenges that we face, and then how does that, how can we extrapolate that into an actual lunar setting? And so any more data that we have from any other landers that aren't on the moon, any samples that we can get, that'll help inform our decisions in that iterative process so that you can be more and more effective
Right.
solution.
We were talking about how the regolith changes from one location to the other about on the moon. And you were saying that you use simulates for different ones. And some of that physically look different. Is that part of that, the fact that the regolith is different?
Yeah, it actually is physically different. Yeah, the composition of the highlands is very different than the composition, mineral composition of the mine. They're just different.
Okay.
It's granite and limestone difference. They're both rocks, yeah, but they're not the same. And so they behave differently. They have completely different constituent properties in them, which changes the melting point. Like we can take the Mare, we can get it melted at about 12 to 1300 C, while the highlands we have to go up to about 1700 C, just because of the constituent minerals in it with higher melting points. And so, yeah, we have to be cognizant of what we have, and that's why it looks different, because it is different.
So is that going to be important for you're going to have multiple different kinds of machines based on where you're going to be landing on the moon?
Well, I think the machines can be very similar. However, the power consumption is going to be different. So, melting the highlands is going to take a lot more power than melting a mine.
Okay.
Similar. And so there's a lot of different considerations on that. And because the temperatures are so different, all of the materials we use will be different. And so the material that we use for mold may work great for a mine at a lower temperature, but would melt if we tried to use that same material on highlands. So if we plan on landing on the South Pole, which is where everybody wants to go right now, because that's where the permanently shadowed regions, VSRs, are,
Right.
that we believe have water, ice on them that we can use for sustainability for humans and other processes that we might be using. Everybody's facing or focusing on the South Pole. And so that's where our focus is right now, is on the highlands. The South Pole is a highlands region around the Shackleton equator. We need to take all of that into consideration, what the local constituent mineral is. So if you land here on a highlands and here on the highlands, they'd be different. When we're talking about ejecta, as it is ejected out and finally settles down, which is much slower on the moon than it is on Earth without the atmosphere and
Right.
once it's gravity and all of that. Some of this can travel all the way around the moon. And so as the meteor strikes the dark side of the moon, whatever is there is now deposited on top of whatever is on our side of the moon. And so over the millennium, we've had this stuff mixed all together. And so different sites would have different constituent minerals.
All right. So I have another question. We're talking about the Lunatron, which is your device that you're working on. It's going to have multiple capabilities. It'll take the sifted regolith. It will be able to melt it and prepare the bricks, and then it will be placing them. But this has a particularly unique shape. Does this shape? Why did you pick this shape? And what does this mean as far as do you need to use mortar to make sure that they're all stuck together, or why? Again, why is it this shape?
This tri-lobe shape is it's kind of a jigsaw puzzle. So they fit together. Doesn't matter how you turn it. So it's a lot more flexible when you're putting it together. And there's an interlocking capability with that shape. As far as the mortar, that is something that we're concerned with. We've done some tests, because as we lay one brick and it cools, we lay the next molten brick next to it. Is it going to fuse?
Okay.
And so we're currently doing tests. We've had it fuse to the existing one, and we've had it not fuse.
Right.
And so we're trying to that iterative process as we're in the infancy. Why did it work here or not? And what are the differences in the environments? What do we do differently? How is this? How can we replicate this? So it fuses every single time. But
So fusing is what your goal is.
well, yes, but we have a backup plan too.
Okay.
And if that doesn't work, well, can we do some laser sintering? Is there some other technology processes that we can use? Can we change this shape into something that has some physical binding properties where it's actually hooked onto the next to it.
Yeah.
Because if we're not careful and we just lay these next to each other and not fused together, there's no water in between, there's no laser sensing, anything going on. So you had a rocket boom on it. And we just made some really big ejections.
Right.
It's been
It's a
fun.
pretty big projectile.
Yes. And that would do some damage to your spacesuit.
Right. Exactly.
And so, yeah, making it one unified mass
Right.
from a bunch of smaller pieces is one of the things we're trying to develop the technology to make that actually happen. It's not an easy process, but like I said, we're in the infancy. We're working toward it, but we'll get there.
Yeah. Well, I think, for fans of Elon Musk, one of the things he talks a lot about is prototypes are easy, production is hard. And for you, production quality needs to be done as well. And it needs to be high enough so you don't have very good rejection rates because, making a landing pad and getting 3 bricks in and realizing 2 that were bad, it's not really.
Yeah, and it's going to be hard to replace those too. Yeah.
So what is your thoughts about that quality control of the bricks as your Lunatron's making them? How would that work?
Yeah, obviously lots of sensors. We're looking at different ways to use some tools. We have some partners that we contacted in Europe that are doing some imaging, I'll call it, that can hear inside, look at the porosity, the structure inside the brick. And so, yeah, we're going to have some QA involved as we're laying this autonomously, where the robot can check it out. Is this good? If not, we got to get this out of here because we don't want rockets to fall over.
Right.
And that's a bad. So, yeah, QA is critical, and having QA in the intelligence, the artificial intelligence, I'm assuming AI, to look at our product, doesn't meet our criteria, and what do we do if it doesn't? And how can we have a good quality every time? How can we maximize our quality and minimize the rejection as much as we can?
Now, you mentioned AI, and the moon is only a couple of seconds light speed away, so it's possible with a little bit of a delay for you to have a human control it here on Earth to help with that process. Do you envision that, or maybe as a stopgap, or do you really want to get to the future where it's completely autonomous? Say if you're on Mars, you don't have that opportunity.
Well, yeah, obviously, our goal is just let the robot do it, and yeah, but there has to be a stopgap because the clock is ticking. And we're going to the moon, and we're going to need a place to land, and we've got to solve this problem. And so, if the solution is the robot takes measurements, sends the data back to someone like you, and you analyze the data, and you go, you know what, looks good, thumbs up, it moves on. And like I said, the light speed, we could do that, and so have some human intervention available if needed. If not, let it do its thing. And I think as time goes on, we can get better and better at it through that process of just learning. And hopefully by the time we get to Mars, we'll have developed the technology to the point where we don't need that rapid human intervention that we might need when we first start.
So with your idea with fusing the bricks together, either with heat or lasers or some other treatment so you have a uniform surface, does that process itself lend itself to having a human 3 to 5 seconds away from being able to say, okay, it's not good or it's good? Or is it such that you have to have it autonomous at the place of that brick?
Well, I obviously we don't have that process worked out and nailed down. This is what we're going to do. But just common sense says, yeah, we're going to start, and we'll probably have to have a lot of human intervention, and we'll get better and better. But so, yeah, the process has to include a human at the very beginning, because I've never made anything perfect the first time.
Right.
And so I haven't made anything perfect the second time either. So as we go on, we'll have less and less human interventions.
All right. Well, it's a humongous challenge. I don't know how many people really think about all of the things that have to happen between making a rocket and landing on the moon to be able to go and live and sustain ourselves. Some people have continued to ask, we went with Apollo, what's the big deal? But this is a completely different deal. And you're part of it.
Mhm. Yeah, I think it's for us to become a multi-planetary species, as some of your viewers may be familiar with. We have to go up there. We have to explore and reach out as human beings, as a species. We need to go out and do this. And the ancillary benefits are incredible. As this technology ripples through our society, into medical fields, into engineering, into terrestrial construction, all of those areas are going to be impacted by this. So I think it's critical that we do this now on the move as soon as we can. And I think I find a sense of urgency in this to get back to the moon.
Right.
For scientific purposes, because we need to know what's out there, but also for humanity, humanity's well-being, our human psyche. I think it's important for us to be able to have that goal, to reach out and have that success. And you can't have that feeling unless you try.
Right.
And so we have to go out there and we have to do this. And it's going to be hard, and there's going to be lots of failures, and that's what we experience here. That's why we do what we do, is we have failure after failure after failure. And failure is not an option, it's a requirement. And if you want to be successful, you have to be willing to do it. I mean, that's what all of this is about.
All right, well, cool. Well, I really appreciate just the opportunity to come and see firsthand what is it like to be making some of these in the lab, trying to work through the numerous challenges to make this a reality. And I think it is very important. And, I wish you the best. And again, thank you very much for having me out here. It's just been a great day.
Well, I really appreciate it. Thanks, sir.
Thank you.
So I hope that you enjoyed this tour of Astroport and some of the information about their plans, their work with NASA, how it may help with the Artemis program, SpaceX's human landing system and Starship going back to the moon, and also sort of the long-term ideas that they have. Of course, it all starts at the laboratory where they manufacture the bricks using simulated lunar regolith. They do a lot of the testing. They look at how vacuum, temperatures, and other constraints that they might face on the lunar surface would affect their ability to make a landing surface. And that's going to be critical if we continue to take people to the moon. We have multiple different landers going to different spots of the moon as well. We're going to need to have some safe places to land. Also, we'll need to have the ability to resupply future bases that hopefully we'll see on the moon. And this is just one of many steps to get to that point. And I just wanted to say thank you very much to Astroport, the people that work here, the CEO, and also with just many of the other people that we've had a chance to meet during this tour, and just giving us a great insight into what does it take to make some of the other important supporting features of missions to the moon that we don't normally hear about. So anyway, I hope that you enjoyed this. I hope it puts it to context a little bit more about what work is being done behind the scenes by companies such as Astroport and many other companies and universities and also governmental agencies trying to solve this issue and get us back to the moon to stay. And as we mentioned earlier, this is very different than what we did with the Apollo era. The Apollo era was great. We got a chance to go to the moon, look around, get some samples, kind of plant the flag, but nothing of that was permanent. So what NASA and all of these companies are trying to do now is significantly different. And that is to return, to stay, build the infrastructure, the support, and also just having that to communications back and forth from the Earth to ensure that the lunar residents are able to stay there healthy without any issues, get that resupply, be able to do science research, and prepare for further explorations throughout our solar system. So thank you again very much for your support and for watching. I very much appreciate it. Take care.